Now we discuss force acting on a current carrying conductor in a magnetic field. For this purpose, we observe some activity, that is, fix a copper wire with the help of stand so that it passes through the pole of the horseshoe magnet as shown in the figure. Connect the circuit as shown in figure. Now, when current is not flowing through the wire, it remains straight. That is position A. When current flows from top to bottom, the wire bends and comes into position C. If the direction of current is reverse, that is, it flows from bottom to top, wire bends and comes into position B. This means the direction of the force on the wire is perpendicular to both the magnetic field and direction of the current. Here, direction of magnetic field is from N to S. It is noted that when current flows through conductor, in the presence of magnetic field, a force is exerted on a conductor. If the direction of the current is reverse, the direction of the force also gets reversed. In above experiment, force is exerted on the current carrying conductor. The direction of this force depends on both the direction of the current and direction of the magnetic field. Now we discuss Fleming's left hand rule, that is straight thumb, forefinger and middle finger in such a way that they are mutually perpendicular to each other. Then thumb pointer gives direction of force, forefinger gives direction of magnetic field and middle finger gives direction of current. This is known as Fleming's left hand rule. Now we discuss principle, construction and working of electric motor, a device which converts electrical energy into mechanical energy is called as electric motor. Electric motor works on principle that current carrying conductor placed in a magnetic field experiences force. Electric motor consists of armature coil, strong magnet, split ring commutator, brushes and battery. We all of us discuss all these points one by one. Number one is armature coil. A large number of turns of insulated copper wire wound on a iron core in a rectangular shape forms an armature coil ABCD as shown in figure. Number two is strong magnet. The armature coil is placed in between two pole pieces of strong magnet. This provides strong magnetic field. Number 3 is split ring commutator. It consists of two holes R1 and R2 of a metallic ring. The ends of the armature coil are connected to these rings. Number 4 is brushes. Two carbon brushes B1 and B2 are used to press the split ring commutator. Number 5 is battery. The battery supplies the electric current to the armature coil. Now we discuss working of the electric motor, that is when current is passed through the coil ABCD, arm AB and arm CD experiences force. According to Fleming's left hand rule, the force experienced by arm AB is in upward direction and arm CD in the downward direction. Both these forces are equal and opposite. These forces rotate the coil in clockwise direction until the coil is vertical. At this position, the contact between split ring commutator and brushes break. So the supply of the coil is cut off. Thus, no force acts on the coil, but coil does not stop due to inertia. It goes on rotating until the split ring commutator again come in contact with brushes B1 and B2. Again current start passing through the coil and arm AB rotate through 90 degree, 180 degree, 270 and 360 degree. Now we discuss electromagnetic induction. We know that if we keep an electric conductor in a magnetic field such that direction of the current flowing through the conductor in perpendicular to the magnetic field, then force is exerted on the conductor. Because of this, conductor moves. But if an electric conductor is moving in a magnetic field, or the magnetic field around a stationary conductor is changing, then what happens? Electric current can be produced in a conductor. This is given by one of the most important scientists, that is Michael Faraday, in 1831. Now we discuss about galvanometer. Galvanometer is a device which is useful for presence or absence of electric current. Specific coil placed in between two poles N and S and connected to knob of galvanometer. Small current pass through it, then knob deflect in any one direction. Deflection of knob depends upon direction of current. Now we discuss one more activity, that is connect circuit as shown in figure. Keep bar magnet below the copper wire. If wire is moved, then what happens? Galvanometer shows the deflection. Now magnet is moved and wire is fixed. Here also galvanometer shows deflection. Similarly, if solenoid coil connected to battery, then what happens? If the current in the coil reaches either steady value or 0, the galvanometer connected to the coil 2 shows no deflection. Thus, potential difference is induced in the coil 2 when the electric current through coil 1 is changing. When current in first coil changes, magnetic field associated with it also changes. Thus, changing magnetic field in the first coil induces current in second coil is called electromagnetic induction. Now we discuss Faraday's laws of induction. So, the number of magnetic lines of force passing through coil changes, current is induced in the coil. This is known as Faraday's laws of induction.